In the Chem Activity 9 and the corresponding videos, we will be looking at the concept of conformations. Conformations are different arrangements in space of the atoms that make up a molecule because of rotation about sigma bonds, or because of the flipping of a ring structure. To give you a sense of what this looks like, let's examine the teaching model number 1. Here the idea is that I'm bringing two carbon atoms together with their sp3 hybrid orbitals, and I'd like to allow the sp3 hybrid orbitals to overlap in a head-to-head way, in other words, to form a sigma bond. Upon forming the sigma bond, there's the possibility then for rotation about that sigma bond. These different rotational arrangements are called conformers. So in the bottom diagram, for instance, if you look at the carbon on the left, our blue hydrogen is stationary. The blue hydrogen on the carbon on the right, however, moves relative to our blue hydrogen on the left. There's a rotation where the blue hydrogen on the right starts in the same plane as the blue hydrogen on the left. And as this rotation occurs, that blue hydrogen comes out towards us and kind of swings around. To give you a sense of what this might look like, I'm going to take you to a molecular modeling software, which is actually part of OpenOChem. The carbon atoms are in gray, and I'm going to click on the rod that holds the two carbon atoms. Of course, that rod represents the sp3 hybrid orbitals in the sigma bond. So now you can see there's a rotation of the hydrogens in the front carbon relative to the hydrogens in the back carbon. Now I'm showing this rotation occurring quite slowly, but actually it occurs, in my understanding, several thousands of times per second. There are an infinite number of possible conformers, but generally we just look at 6 different conformers because they represent the energy extreme. Now there's a convention to represent the different conformers, and so I'm going to introduce this idea of drawing a Newman projection. So the diagrams on the left show a wedge and dash representation of a particular conformer, and you can see that I've tried to draw in an eyeball, and the idea is that I want to look down the axes of the front carbon to the back carbon. So let's call our front carbon carbon number 1 and the back carbon carbon number 2, and it's the same molecule and the same conformer in both of those drawings. Now the idea is that we focus on the front carbon here, which I'm circling, that's carbon number 1, and we represent what that would look like if we were looking down the axes of 1 down to 2. Our front carbon would show something like what's drawn where I've just highlighted the red dot. That is, we'd see the hydrogens arrange themselves in something like a Y shape. So that represents the front carbon and the corresponding hydrogens. The back carbon would be similar, but you can see the hydrogens are in a different position. So that we can see the back carbon, so in other words carbon number 2, we use this larger circle. So just to clarify, this would be carbon number 1, and this would be carbon number 2. And again, to help clarify, and maybe I'll change my pen color just to be consistent. So here's our blue hydrogen on carbon number 1, and here's the blue hydrogen again. And in terms of the blue hydrogen on carbon number 2, here it is in the wedge and dash, and then here it is as part of the Newman projection. So the idea is that we bring these two portions together and draw a structure that represents both carbons 1 and 2, and this is referred to as a Newman projection. Now for a molecule like ethane, there's really only one Newman projection. That is, you can only look down carbons 1 to 2, although there be several conformers that can be represented with that Newman projection. But of course, if you have more carbons, well then you could look down between carbons 1 and 2, down 2 to 3, down 4 to 5. So you can imagine this could get quite complex. So if I ask you to take a wedge and dash drawing and change it into a Newman projection, this is what you would do. Now we can also, however, start from a Newman projection and translate it into a wedge and dash. So let's take a look. So in this key question number 1, I comment that the representation in teaching model number 2 shows ethane in the lowest possible energy, in other words, the most favorable conformation. Now here's another Newman projection written on the left-hand part of your screen, and you can see that the hydrogens in this conformation are actually overlapping, and as a result, this corresponds to the least favorable conformation. Now I'd like to translate this into the wedge and dash structure. So the idea is, once again, we need to understand our perspective. So I'm going to draw an eyeball, and I'm going to say, I'm looking from this side. Now, of course, you can look from any side that you wish, but you need to establish that you're going to look from one particular side. And let's call this carbon number 1, and this will be carbon number 2. So if I'm looking from the right-hand side towards the left, my carbon number 1 will actually be to the left of my field of vision. So now I'm going to show carbon number 1. And I would see that actually there's a hydrogen rising out of carbon number 1. And then there would be the sigma bond between carbons 1 and 2. And then there would be another hydrogen rising out of carbon number 2. So this would be carbon 1. This would be carbon number 2. The other hydrogens I would need to represent in 3 dimensions. In other words, using the wedge and dash. On carbon number 1, there'd be a hydrogen coming out at me. So just to clarify, this hydrogen would be this hydrogen right here. That would be coming out at me and towards my left. There would, of course, be a hydrogen going back. On carbon number 2, there would also be a hydrogen coming out at me and a hydrogen going back. Both of these representations, that is the Newman projection as well as the wedge and dash, represent a single conformer. Both can be used. Sometimes it's preferable to use the Newman projection in certain situations. Sometimes it's easier to use the wedge and dash. And you'll see as you start to work with these when one representation is more appropriate than the other. In this table, I compare the 2 different major kinds of conformers for the molecule ethane. So we've got the staggered versus the eclipsed. And we'll focus on, let's say, a pair of hydrogens, one found on the front carbon and one found on the back carbon. Maybe we should look at the eclipsed first of all. So you can see in the eclipsed conformation, the hydrogens overlap one another. And as a result, we would say that the torsional angle is 0. That is the angle of the front hydrogen compared to the back hydrogen. By contrast, in the staggered conformation, we're going to compare this hydrogen to this hydrogen and consider this angle right here, which I hope you will agree with me is 60 degrees. So we'd say the torsional angle for a staggered is 60 degrees. So you're always comparing one thing in the front carbon compared to one thing in the back carbon. In this case, it's the hydrogens. Now we would say that the eclipsed conformer has torsional strain, and this is due to the repulsion of bonding electrons on one substituent as they pass close to the bonding electrons on another substituent. In other words, and let me just change my pen color so we can see this more easily. So we're talking about the repulsion of the electrons found in the bond between the carbon and the hydrogen in the front carbon and the electrons in the carbon-hydrogen bond in the back carbon. So it's a repulsion between these pairs of electrons. So it's less about the repulsion between the hydrogens, but rather repulsion between the pairs of electrons. And of course, I've just highlighted the repulsion between those bonds. There would also be a repulsion, and maybe I'll just again change my pen color. There would be a repulsion between the carbon-hydrogen bond in the front carbon and the carbon-hydrogen bond in the back carbon. Okay, so there would be all of this repulsion happening. And therefore we would say that there's this torsional strain. The staggered conformation represents a situation where we would say there is 0 torsional strain, because the bonding electrons of the carbon-hydrogen bond in the front carbon right here are skewed or away from the bonding electrons between the carbon and the hydrogen on the back carbon. They're maximally distanced from one another. So therefore we would say zero torsional strain.